friends, my name is Amita and in this video I am going to discuss about another commutation technique, that is a class C commutation. I hope you are aware about the commutation, but if you are not aware, then I just want to tell you that commutation is nothing but it is the process by which already conducting SCR can be off, or it is a process in which the SCR changes its state from forward conduction mode to forward locking mode. There are two methods of commutation. One is called as a natural commutation, which occurs when the connected supply to the SCR is AC. As AC by nature, it passes through zero 2 times in one complete cycle. When the AC completes its positive cycle and when it crosses through zero and later on it goes into negative cycle, that will be the instant when, if the load connected to the SCR is resistive, the SCR will be automatically off because of the connected supply. So that kind of commutation is called as a natural commutation, because we have not used any external circuit, neither we have created any artificial conditions to make the SCR off. It will be automatically off due to the nature of a AC supply. That's why it is called natural commutation. Whereas if I talk about the second type of commutation, that is a forced commutation. As the name indicates, in this kind of commutation, with the help of some external circuit, that is called as a commutation circuit, we artificially create the favorable conditions to make the SCR off, and those conditions are that we develop the voltage across SCR in reverse bias condition, and at the same time we try to make the current flowing through SCR zero. So when these two conditions fulfill, then the SCR will be off. So that kind of commutation is called as a forced commutation. There are two varieties of a forced commutation. One is a voltage commutation, another is a current commutation. As the name indicates, voltage commutation, we create a voltage across the capacitor, and that voltage across capacitor, by some circuit, we try to appear across the already conducting SCRs for a sufficient duration in a reverse bias condition. So because of a reverse voltage across the SCR, a device will of that kind of commutation is called as a voltage commutation. Similarly, if we try to make the current flowing through SCR zero by some external circuit, then because of the current is zero, when current is zero means the device is acting as an open circuit. So that kind of commutation is called as a current commutation. In my previous videos, I discussed about two commutation. The link for the same is given in the description. One I have already discussed about in class C commutation, that is the external pulse commutation. It is a variety of voltage commutation. Second, I have given the description of a video for a class D commutation, that is also a voltage commutation. Now in this video, I am going to discuss about the class C commutation, which is also called as a complementary commutation, and it is a type of a force commutation, and in a force it is a voltage commutation. Now your question can be, why we are having so many topologies of a commutation circuit for a voltage commutation? The reason is that if we apply a voltage commutation technique to make the SCR off, the time taken for the turning off of SCR is less in comparison to the current commutation technique. That's why a lot of topologies are there for a voltage commutation methods. So now I am sharing my screen where I will brief you the class C commutation. I will start with some facts of a class C commutation, then we'll discuss about its power circuit diagram and the operation. So let us discuss about class C commutation. This is also called as a complementary commutation. Commutation. Why it is called complementary commutation? When I will discuss its power circuit diagram, it will be clear to you. So the first fact about it, it is a type of force commutation. That means by using this technique, you can turn off the SCR when it is connected to positive supply as well as it is connected to DC supply. And in force commutation, it is a kind of voltage commutation technique. Voltage commutation technique. And the commutating element which we use in this commutating element is capacitor. So this is something about the brief description. Now let us talk about its power circuit diagram, or you can say it is the topology of a class C commutation. There is a resistance R1, there is a resistance R2, and here we connect one capacitor. Here there is a thyristor 1 or SCR1. This is SCR2. So this is capacitor. This is T1. This is T2. And here we connect the supply voltage, that is DC type, and it is Vs. So if I see the power circuit diagram, it is having two resistances. R1, R2 are the resistances, C is the capacitor, and T1 and T2, they are the SC. So this is something about the power circuit diagram of a class C commutation. Now let us understand its operation. So before understanding its operation, there are few assumptions. Number one assumption is all SCRs, that is T1 and T2, both are ideal devices. Ideal devices means when they are turned on, they will act as a short circuit. There will not be any turn on resistance. The second thing is load current is constant. Okay. Now let us discuss about its operation. If I want to tell about its operation, that explain its operation by dividing into a various operating modes. So let us have a mode 1 which exists between 0 to T1, and in mode 1 T1 is on and T2 is off. So the equivalent circuit will be, this is your resistance R1, this is your resistance R2. Here it is a capacitor. T1 is on means it will act as a short circuit, and T2 is off means it will act as an open circuit. This is T2, this is T1. And here the supply voltage is connected, that is Vs. This is plus, this is minus. Now under this condition, you can see there are two paths for the flow of current. One current can flow like this. Okay, as this current is passing through R1, so I am representing this by I1. And the second current which I am representing by white color, that current can flow through R2, then passes through C, and then passes through T1, and then return to minus Vs. Since this current is passing through R2, so I am representing by I2. Now, if I want to give the expression for these currents, I1, that is equal to Vs by R1. Because what is the voltage across this? That is Vs. And what is the resistance of this part? R1. So I1 will be Vs by R1. I2, as you can see, I2 is flowing through a RC circuit. And in RC circuit, the expression of current, that is equal to Vs R2, Vs by R2 e की power minus T by R2C. Now how this expression comes into picture? If you want to see the detail of this, kindly see my another video which is mainly focused on that when a DC source is connected to a series RC circuit, what will be the expression of current. The description of that video is given in description. You can refer that video and you can see how this expression of current comes into existence. Now, this is also equal to IC. You can see that I2 is also passing through capacitor also. So this is also equal to IC. Now, if I want to plot this current, you can see here when t is equal to 0 means e ki power minus 0. E ki power 0 means 1. So what will be at, suppose this axis is t, and suppose if I am representing here I2, that is equal to IC. So what is the initial current? Vs by R2. And when t is equal to infinite, e ki power infinite is 0. And in between it will vary by this expression. So means exponentially decaying, and somewhere at t is equal to infinite, the current will be 0. So this is how the variation of current I2 or the charging current will be there. Now when this current is flowing through the capacitor, we know the voltage across capacitor is given by this expression 1 by C integration 0 to t IC dt. So when I put this IC from here, and if I solve it and put the limit, I will get this expression Vs 1 minus e ki power minus t by R2C. So this is how the capacitor voltage is going to change. Now when I put t is equal to 0, e ki power 0, so that means e ki power 0 is 1. So 1 minus 1 is 0. So if I plot the capacitor voltage, at 0 the capacitor voltage will be 0, and when t is equal to infinite, e ki power infinite is 0. So what is the, at somewhere at infinite, it will be Vs, and in between it will vary by this expression. So this is how the capacitor voltage is going to change. Now at the end of mode 1, at the end of mode 1, which is the beginning of mode 2 also, beginning of mode 2, what is the circuit situation? At the end of mode 1, Vc is going to have an Vs value with right plate of capacitor positive, right plate positive, and left plate negative. Left plate negative is the capacitor. You can see, since the current flowing through capacitor is right to left, so of course this will be, so of course this end will be positive and this end will be negative. So it will charge with this polarity by a voltage of Vs. And at the end of mode 1, as the capacitor is charged by the voltage of Vs, there will not be any potential difference, because this is plus Vs, this is plus Vs. So there will not be any potential difference. So the charging current at the end of mode 1, it will be 0. Now, one more thing I want to tell you, as I1 and I2 both are flowing through T1. So what is the value of IT1? That is I1 plus I2. So I1 is Vs by R1 and I2 is Vs by R2 e ki power minus t by R2c. So at the end of mode 1, as IC is 0, so what is your IT1? IT1 will be Vs by R1 as I2 or IC is equal to 0. So this is the situation at the end of mode 1. Now let us talk about mode 2. So mode 2 exists between T1 to T2, T2. Now, as I already mentioned that at the mode 2 beginning will be the mode 1 end situation. So this is the circuit, this is R2, this is R1. Now this is T1, this is T2. Mode 1, at the end of mode 1, this is plus, this is minus, and this is Vs. And you can see that T1 is acting as a short circuit in mode 2 and T2 is acting as an open circuit. Now under the condition, there is only one current can flow, that is this I1. And what will be the value of I2? As I2 will be, in this case, will be 0. Why 0? Because this is plus Vs, this is plus Vs, so there will not be any potential difference here. So when the potential difference is not there, then the current will be 0. And I2 is also equal to IC, so IC will also be 0. At the same time, the I1 will be Vs by R1 and IT1 will be I1 plus I2. So that is also equal to Vs by R1. In this case, as there is no charging current flowing, so Vs will remain sustained at Vs, means its value will be constant at Vs, means whatever the value of Vc is there at the end of mode 1, that will remain sustained during mode 2 also. So this is something about mode 2, and in this mode Vt1 is 0. And what is Vt2? Vt2, you can see here, whatever the capacitor voltage is there, through this T1 short circuit is appearing to T2. Now positive capacitor voltage is appearing here and negative is appearing here. So Vt2 is also equal to a capacitor voltage, and it will be plus Vs constant, as the capacitor voltage is constant in this mode, so it will be constant. Why I am writing plus Vs? Because this capacitor voltage is appearing to T2 in a forward bias condition. At the same time, if I will write it for the mode 1, if I write in mode 1, what will be the Vt1? In mode 1, Vt1 will be 0 and Vt2 will be equal to Vc. Means as the Vc is changing, in a similar fashion, Vt2 is changing. So this is something about mode 2. Now let us talk about the next mode, that is third mode, mode 3, which exists from T2 to T2, T3. Now T2, in this mode, T2 is triggered because T2 is already forward bias at the end of mode 1 and it was remaining forward bias in mode 2, but it was not on as the triggering pulse is not given to T2. So at the beginning of mode 2, the gate pulse is given to T2. Now what will happen? As we give the triggering pulse to T2, now see what happened. So T2 will be now on. And as we give the triggering pulse to T2, since the voltage across the capacitor was like this, so through this T2 short circuit, the plus is appearing to the cathode of our T1 and negative is appearing to the anode of our T1. So this T1 is reverse bias and that's why it will be off. So why it is called complementary commutation? It is called complementary commutation because if the T1 is on, T2 has to be off. If T2 is on, T1 has to be off. So they are complementing to each other. That's why this method of commutation is called as an complementary commutation. Now this is the situation of the circuit. Now in this case, if I plot I1 will flow like this, that I have shown with the red color, and I2 I will show with white color. So I2 will flow like this. This is I2. Now in this case, I2 is passing through T2 and R2. So that will be Vs by R2. And in this case, I1 is the current which is passing through capacitor also. So I1 is equal to IC. And as this I1 is passing through RC circuit, so whenever the DC source is connected to RC circuit, I already told you that the current expression will be given by Vs by R1 e to the power minus T by R1C. Now here it will not be Vs by R1, it will be 2 Vs by R1 because the capacitor is already charged by the voltage of Vs under this condition. So when we are going to write its KVL equation, we are going to write Vs is equal to R1 I1 plus 1 by C integration I1 dt and minus Vs. So when you solve it, you will get this expression of current. Now when this IC is there, as the current is flowing from now left to right, so what is the capacitor voltage? Capacitor voltage at any time we give by this expression. So 2 Vs by R1 e to the power minus t by R1C. So if you solve it, it will come 2 Vs 1 minus e to the power minus t R1C. This is the expression for the capacitor voltage. So that's it. And now at the end of mode 3, at the end of mode 3, that will be the beginning of mode 4 also. Beginning of mode 4, what is VC? VC will charge by minus VS. Okay, IC will be 0 at the end of this mode. IT1 will be 0. Yeah, one more thing. In this mode, IT1 that will be equal to 0. IT2 that will be equal to I1 plus I2. So I1 in this case that is 2 Vs by R1 e to the power minus t by R1C plus Vs by R2. VT1 in this mode will be VC. As the VC is changing, in a similar fashion VT1 is changing, and VT2 in this mode will be 0. Now at the end of this mode, mode 3, what is IT1? IT1 at any time that is equal to I1 plus I2, and here IC is equal to I1. So I1 is 0 means it is only equal to I2. And what is I2? Vs by R2. And what is VT1? That is minus Vs. And what is VT2? That is 0. So that is the situation at the end of mode 3. Now the next mode, that is mode 4. Mode 4 exists between T3 to T2, T4. Now at the end of mode 3, what is the situation? The capacitor is charged by minus Vs voltage, means now the left plate is positive and right plate is negative. This is Vs and this is capacitor. T1 is still off and T2 is on. So T1 and T2. Now under the condition, as now the capacitor voltage through T2 circuit is appearing as a forward bias, but still the T1 is not on because the triggering pulse is not given to it. So under the condition, only one current can flow, that is this I2. IC will be 0 in this case. Why? Because this is plus Vs, this is plus Vs. So there is no potential difference. So in this case, I1 is equal to 0 and IC is equal to 0. Only I2 will flow and that is equal to Vs by R2. IT2 is equal to only Vs by R2 because IT2 is equal to I1 plus I2. As I1 is 0, so that is equal to only I2. And Vc will remain sustain its value at minus Vs because the charging current is 0. VT2 in this mode will be 0 and VT1 will sustain at plus Vs. Why I am writing plus Vs? Because this capacitor voltage is appearing to T1 as a forward bias condition. So this is something about the mode 1. Now as the capacitor voltage is now making the thyristor T1 forward bias, so this once we will give the firing pulse to T1, then T1 will be on and T2 will be off. So means we will reach to the mode 1. And again mode 1 ke baad mode 2, then mode 3, then mode 4. So it will goes into closed loop. So this is something about its complete operation. Now let us try to make the waveforms. So let me tell you the waveforms. So first I am drawing the axis. So this is 0, this is T1, this is T2, this is T3 and this is T4. So this is mode 1, mode 2, so this is mode 1, this is mode 2, this is mode 3, and mode 4. So this is again mode 1, mode 2. Now Let me tell you here I am going to plot IG1. Here I am going to plot IG2. This is IC. This is VC. Here IT1. Here I am going to plot VT1. This is VT. No. IG1. IG1 means the gate pulse given to SCR1. So as the SCR1 is at t is equal to 0, SCR1 is on at t is equal to 0, so the gate pulse we will give at the beginning of mode 1. SCR2 is on at the beginning of mode 3, so we will give the triggering pulse at t. Now what is IC? IC in the mode 1, that I already told you that it varies by the expression of Vs by R1 e to power minus t, Vs by R2 e to power minus t by R2c. So at the beginning, the current will be Vs by R2, and at the end of this mode, the current will be 0. And in between, it will vary by expression of Vs by R2 e to power minus t by R2. Now what is Vc? Vc at the beginning it will be 0 and it will be charged by a voltage of Vs, and in between it will vary by the expression of 1 minus Vs1 minus e to power minus t by R2c. Now what is IT1? IT1 is the addition of I1 plus IC. I1 is Vs by R1. So that means it will be this IT1 is nothing but it is IC uplifted by Vs by R1. So that means its initial value will be Vs by R1 plus Vs by R2, and it will be exponentially decaying up to Vs by R1. And in between, it will vary by the expression of Vs by R1 plus Vs by R2 e to power minus t by R2c. So this is how it is going to vary. Now, in mode 2 mein what is IC? IC is 0. What is VC? It will sustain its value at Vs. And what is IT1? It will sustain its value at Vs by R1. Now, let us talk about mode 3. So, let me rub this part. Okay. So, in mode 3, what is IC? In mode 3, I have already told you in mode 3, now I1 will be your IC and its value will be, initial value will be 2 Vs by R1 and it will be exponentially decaying up to 0, and in between it will give by the expression of 2 Vs by R1 e to power minus t by R1c. And what is capacitor voltage? It will be exponentially decaying its value. It will change its value from plus Vs to minus Vs. And in between, it will vary by the expression of 2 Vs, 1 minus e to power minus t by R1c. Now, what is IT1 in this mode? IT1 in this mode will be 0. Now, what about mode 4? Mode 4 mein IC is 0. It will sustain its value at minus Vs and IT1 will be 0. So, this is the waveform of IG1, IG2, IC, VC and IT1. Now, if I want to plot VT1 and VT2, since in mode 1, VT1 is on, so it will be 0. Mode 2 also VT1 is on, so it will be 0. Now, mode 3 mein, why in mode 3 the T1 is off? Because the capacitor voltage is appearing through the short circuit of T2 to T1 as a reverse bias. So that means it will be reverse bias. The voltage across T1 is minus Vs and it will change its value just the inverse of this. So as the capacitor voltage changes its value from plus Vs to minus Vs, but when it appeared to T1, it will change its value from minus Vs to plus Vs, and then it will be plus Vs. So this is Vt1. Now Vt2, in mode 1, in mode 3 and 4, as the T2 is conducting, so it will be 0. Mode 1 mein, why the T2 is off? Because the capacitor voltage is appearing to through T1 short circuit to T2. So mode 1 में the capacitor voltage changes its value from minus V from 0 to plus Vs. So it will be like this, 0 to plus Vs, and then it will be second mode mein, it will be Vs, and after that at the beginning of mode 3, as we have given the triggering pulse to this, so it will be C. So this is something about Vt2. So I hope these waveforms are clear to you. Now I am stop sharing my screen. I hope whatever information I have shared in this video related to an class C commutation, that will be clear to you. Why it is called complementary commutation? Because you have seen in the mode 1 when the T1 was on, T2 was off. And as soon as in the mode 3 at the beginning, as we give the triggering pulse to T2, so at the same instant the T1 is off. So that means if T1 is on, T2 has to be off, and if T2 is on, T1 has to be off. That means these two SCRs are complement to each other. If one is on, another has to be off. So that's why this is called complementary commutation. Now why it is called as a voltage commutation? Because we have seen that we have built up the voltage across the capacitor with a different polarity, and that polarity of a capacitor voltage we are trying to appear to the SCR in a reverse bias condition. Because of that the SCR is off. Like we have seen in the mode 3, the capacitor voltage polarity through the T2 short circuit we were appearing to T1, and because of that reverse voltage the T1 is off. So that's why since the SCRs are off, they are making off because of the reverse applied voltage across it. That's why it is a voltage commutation. I hope now the class C commutation is clear to you. If you like this video, kindly press the like button, and if you feel that whenever I make such kind of videos related to power electronics, a notification should reach to you, then don't forget to subscribe my channel.